All right, so we're taking a look at practice exam for Chem 251, Unit 1. All right, so the first couple here are nomenclature. Write the name or structure below. First one, most important thing for these the cycle rings is find the ring is the parent chain always. The ring is the parent chain. So it's cyclopropane. Chloro takes priority. 1 chloro, 2 ethyl, cyclopropane. Butanamine, again, find the parent chain. The parent chain is the longest chain with nitrogen and carbons. 1, 2, 3, 4, butane. So 4 carbons, then the nitrogen. And propyl, 1, 2, 3, propyl group. And then what's left? Nitrogen needs to have 3 bonds, so there needs to be an H there. Next one. This alcohol is one of the longest chain with the alcohol in it. So 1, 2, 3, 4, 5. So it's a pentanol. So that eliminates A and B. And then alcohol takes priority. So we have number this way. 1, 2, 3. So it's 2 pentanol, 3 methyl. All right, moving on. Wedges and hatches on a ring. Which chair does it match with? So the OH, I like to think is up, is wedged. Chlorine and methyl are on the same side. They're both hatched, so they're both down. So it matches this one. So OH is up and axial. These are both down equatorial. Methyl and OH on the same side, so that's wrong. They're all down here. And chlorine and OH are up on the same side here, so it has to be this one. Count the carbons. Hopefully simple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What type of orbital overlap for a sigma bond? So you got to know the hybridization states of these two, between the nitrogen and carbon. So this nitrogen is sp2 hybridized. It's using an sp2 hybrid orbital to make this sigma bond. The same with this carbon, it's also using sp2 hybrid orbital to make this sigma bond, so it's sp2. Remember, p orbitals can only make pi bonds, so they never make sigma bonds. Another one about drawing in arrows and lone pairs. So again, just knowing some periodic table trends. If bromine has a full octet, it has a negative charge. If oxygen has a full octet with 3 bonds and a lone pair, it has a plus charge. Looking at bonds, broken bonds formed here. Right, you can see this bromine all of a sudden is bonded to carbon 3, right there. Right, and the reason I know this is carbon 3 is because that's the carbon that's bonded to the oxygen, which even though if the oxygen has a plus charge, it's actually it's not electron deficient. It's the molecules next to it. So in this case, carbon 3 is the electrophile, bromine's the nucleophile. Right, also labeled there. The arrow is showing the electrons going here to form the bond between bromine and carbon 3. This bond shows a carbon 3 and oxygen 2 bonds breaking. Right, and oxygen gets that other lone pair, and those are the 2 electrons are coming from that bond. Make sure you label specific atoms, and on the left, electrophile and nucleophile. All right, for these ones, probably helps to have a person drawn, maybe. It helps you where your feet and hands are at, where you're looking down 1 to 2. So carbon 1 at its feet has an ethyl. That's the front carbon. Fluorines on the right-hand side, iodine's on my left. If I look back to carbon 2, there's a CH3 right here, pointed up. Carbon 2 is the big circle. Iodine to my left, H to my right. So you got to go from here to here first. Then it says rotate carbon 1 counterclockwise. That means the back carbon 2 never will change for all of these. So it's the same thing every time. So that never changes. Counterclockwise means to the left. So I go from a staggered conformation to an eclipse. So now the fluorine's here. Iodine's onto the other iodine. That's there. All right. Again, counterclockwise, back stays the same. Then we go from eclipse to staggered. Everybody moves around 60 degrees. Staggered, go to eclipse again, and we are done. Except now, we need to take this final one and redraw it. Right? So if I redraw it, so that's carbon 1 in the front, 2's in the back. Right? 1 was in the front, always 2 in the back. So if I'm looking at this straight on, I have the 2 things in my head, so it's eclipsed. So there's the ethyl and carbon 1, methyl. My left-hand side, it's a fluorine. The front carbon 1, iodine and carbon 2. My right-hand side, iodine and carbon 1, and H on carbon 2. Numbering your atoms and showing me what you know what's going on is a key part here. All right, for these ones, match reactions. So we have 4 types of reactions we learned about: addition, substitution, elimination, or rearrangement. So rearrangements, we go from a cis to trans, 3D space. That's a rearrangement. Substitution, you're trading out one set of atoms for another. So you trade the bromine here for this. That's substitution. Elimination, you make a pi bond. So that's an elimination. Addition is when you add 2 things across a pi bond. So that's an addition reaction. So for this one, draw the mechanism arrows on the starting materials to form the product. So I need arrows here. So nucleophile and electrophile. Right, which bonds need to be formed, which bonds need to be broken. I need to make a new NH bond, and I need to break an OH bond. So electrons are going to flow from the negatively charged nitrogen, because that's going to be forming a new bond there. The electrons between its OH bond are going to go to the oxygen, and that's what's going to have more electrons there. So that's a negative charge now. And which is going to be favored? So the products are favored because oxygen's more electronegative. They both, this negative nitrogen could do resonance, and so could this. But that doesn't, so there's no difference there in the resonance. So you could look at the oxygen being more electronegative, more stable, or you could have drawn resonance and shown that this bond is also more polar and the starting materials are more reactive. All right, for number 7, draw 3 potential resonance arrows, or resonance structures. All right, so again, recognize these patterns. If you see lone pairs on an atom and no charge, when you do resonance form, you're probably gonna put lone pairs on another atom. Again, I'll have to have p orbitals, so I lined everything up. I numbered the ones that are all the p orbitals lined up. All right, notice I can't go this way because that's sp3 hybridized. No p orbital. Only atoms with p orbitals can do resonance. Lone pair goes there to form a new pi bond between 1 and 2. Breaks the pi bond. Both those 2 electrons in that pi bond go to carbon 3. So now there's a plus charge on oxygen, a negative charge on this carbon because it has a lone pair now. Those electrons move to create a new pi bond between 3 and 4. Pi bond between 4 and 5 breaks. The electrons go to 5. Keep balancing our charge. Nothing happened over here, so that just stays the same. It's oxygen, so it's a plus charge. Electrons, lone pair on 5, now go between 5 and 6. Pi bond between 6 and 7 breaks, and electrons go to 7. All right, always balancing our charge, always moving electrons in p orbitals. All right, hybridization states. So this is usually we ask ourselves what kind of bonds an atom has. Does it have any pi bonds? So we look at this nitrogen. It has 2 pi bonds. We know that has to be sp because it needs to have 2 hybrid p orbitals. Look at this carbon. It has 1 pi bond. So we know it has to be sp2 because it needs 1 p orbital. This oxygen, though, is a little tricky. Any atom that has lone pairs that's next to a pi bond, right? Oxygen has lone pairs next to a pi bond. We know that that atom is going to be sp2 hybridized, so it can do resonance, so it has a p orbital. So that's oxygen's sp2 hybridized. Rankings. All right, so for these ones, we want to start with the middle. All right, we're going to usually rank by atomic number. This one's a little tougher because it's carbon, 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 so it's all a tie. So we need to look at what each of these carbons is bonded to. So this carbon is bonded to a bromine, an H, and an H. This carbon is bonded to an H, an H, and an H. This one's bonded to a carbon, an H, and an H, right? We're seeing going out one bond at a time. Carbon, a carbon, and an H. Mess that up. This carbon is bonded to a carbon, an H, and an H. Right? This carbon is bonded to a carbon, an H, and an H. Yes, there's oxygen out here, but we only go one bond out at a time. So that means this has the highest priority because bromine is the highest atomic number. This has lowest because hydrogen is lower than carbon. And these two will tie and tie, but then all of a sudden this will win. So that's white. That's number 2, right? This carbon beats that hydrogen. So these are the rankings. And then if you use your model kit, you should see that it rotates clockwise, so the molecule is R. Similarly, down here it's a little easier because this is just looking at atomic number. So you have sulfur as the highest atomic number, then phosphorus, then oxygen, then carbon. So 1, 2, 3, 4. And if you do the model kit rotating, this is actually an S molecule. Make sure you take time to rank these things and do your best. All right, getting to the end here. A little chair flip. So we start with this chair instead of the middle. Drive it to a cyclohexane ring with wedges and hatches, and then do a flip to the left. So let's do the wedges and hatches first. I see this as down, and I'm not numbering. I'm just going to number here to keep track of my things. It's not a naming, but just numbering. So there's 1, 2, 3, 4, 5, 6. So I put things in the right places. Same deal here. 1, 2, 3, 4, 5, 6. OH is down, so I like to make that hatched. On carbon 3, the ethyl, there's 2 carbons here, is wedged, so that's up. And fluorine is up as well on carbon 4. So there's that is. On the ring flip, if you're down, you stay down. If you're up, you stay up. But you switch from equatorial to axial or vice versa. This OH is equatorial down, so now it's going to be axial down. Ethyl, this ethyl is axial up, so now it's going to be equatorial up. So the first bond is up, another carbon there. Fluorine is equatorial up, and now it's going to be axial up. So there you go. Last one, drawing some arrows. Make sure, right, redrawing the first structure can make things clear, so make sure that might be a helpful thing there. What are you going to do? Lone pairs, go towards there, make a pi bond, break that towards the electronegative oxygen. All right, so that's one we've seen before. Doing exactly the same thing on the other side. Move the electrons from here, make a pi bond, break a pi bond, balancing our charges, so go from no charge to charge. Keeping track of lone pairs, keeping track of charges. That's the key. For this one, the final one, this is just an acid-base one, so you see the products. All of a sudden, that hidden H gets taken off of there, so it's a negative charge there, and this carbon right here gets an H, so this is the conjugate acid. In this case, the electrons here go and grab that H to form that new CH bond. The electrons in this CH bond become the lone pair on that negatively charged carbon as the final product.